The cosmos waits for no one. For SpaceX, the year 2027 looms large. It is not just a date on a calendar, it is a critical deadline for the Starship program. The goal is clear: achieve reliable orbital flight. This is the key that unlocks the next chapter of human space exploration. NASA is watching closely. The Artemis program, which aims to return humans to the moon, depends on Starship. It is the designated lunar lander. Without a proven spacefaring Starship, the dream of walking on the lunar surface once more remains just that, a dream. The pressure is immense, a cosmic race against time itself, pushing engineers and scientists to their absolute limits. Each test flight is a step on this long journey. But space is unforgiving. Every explosion, every anomaly, every mission that ends short of its goals is a potential delay. Consider the recent test involving Starship 36. Its dramatic end was a stark reminder of the challenges. These events are not just spectacular displays of fire and force. They represent lost time and resources. They push the 2027 timeline further into the future. For NASA, this means their own carefully planned schedules for the Artemis missions might need to be rewritten. The entire architecture of our return to the moon is interconnected, and Starship is a foundational piece of that grand puzzle. The stakes are higher than just reaching a single destination. Starship represents a paradigm shift in our access to space. Its promise of full and rapid reusability could lower the cost of reaching orbit by orders of magnitude. This would make space accessible in ways we can only begin to imagine. It could lead to cities on Mars, scientific outposts on the moon, and a bustling economy in low Earth orbit. But first, it must fly. It must prove it can reliably leave Earth and return safely. Every setback, while a learning opportunity, also adds a delay to this revolutionary future, keeping it tantalizingly out of our grasp for just a little longer. So, when we look at the fiery end of a prototype, we see more than a failed test. We see a ripple effect through the entire space industry. We see the direct impact on national goals and international collaborations. The journey to orbit is not a straight line. It is a winding path filled with both triumphant successes and explosive failures. The challenge for SpaceX is to navigate this path efficiently. They must learn from every mistake and keep moving forward, always with an eye on that 2027 deadline. The future of humanity as a multiplanetary species may very well depend on their ability to conquer these immense challenges. SpaceX has a unique philosophy. They embrace failure, not because they want it, but because they understand its value as a teacher. When a rocket like Starship 36 explodes, the mission is not over. In many ways, it has just begun. The first step is to gather the data. Thousands of sensors on the vehicle record everything. They measure temperature, pressure, vibration, and a million other variables. This information is a treasure trove. It is a digital ghost of the rocket, telling the story of its final moments. Engineers pore over this data, looking for the single tiny anomaly that started the cascade of failure. Once the data points to a potential cause, the real work starts. This is a process of deep investigation. Teams of engineers analyze the telemetry, review high-speed camera footage, and examine any recovered debris. They are cosmic detectives solving a complex mystery. Did a valve fail to close? Was there a structural weakness in a weld? Did a Raptor engine perform outside its expected parameters? Finding the root cause is everything. It is the difference between repeating a mistake and moving past it. This meticulous process ensures that the next rocket built will not suffer the same fate. It is a cycle of testing, failing, analyzing, and improving. This iterative design process is what allows SpaceX to move so quickly. Instead of spending years designing a perfect rocket on paper, they build and fly. They learn from real-world physics, not just simulations. Each failure provides crucial insights that are fed directly back into the design of the next generation of ships and boosters. This is why we see constant changes and upgrades with each new prototype that rolls out of the factory. The lessons learned from one explosion are physically built into the hardware of its successor. This rhythm of rapid innovation is the engine driving the Starship program forward. This approach is fundamentally different from traditional aerospace development. It is more akin to software development, with its cycles of releases and patches. A rocket is treated not as a precious, one-of-a-kind machine, but as another step in an evolutionary process. The goal is not to avoid failure at all costs, but to fail fast and learn faster. This mindset is what turns a spectacular explosion from a catastrophic setback into a valuable data point on the path to success. It is a powerful, if sometimes fiery way to climb the ladder to the stars, one rung at a time. Down in South Texas, at a facility called Starbase, the future is being built around the clock. It is a scene of constant activity, a factory for giants. Here, new starships and their massive super heavy boosters rise from stainless steel rings. The pace is relentless. As soon as one test campaign ends, hardware for the next is already being prepared. We are now seeing the assembly of Starship 37. This vehicle is not just a replacement, it is an evolution. It incorporates all the hard-won lessons from its predecessors, including the data gathered from the flight of Ship 36. Every weld and every wire is a testament to the lessons learned. Beyond individual ships, SpaceX is working on major block upgrades. The move to Block 3 starships represents a significant leap in design and capability. These are not just minor tweaks. They involve fundamental changes to the structure, the engines, and the life support systems needed for future crews. Structure, engines, life support systems. The goal is to create a more robust and reliable vehicle, a rocket that is easier to manufacture, easier to refurbish, and ultimately, safer to fly. Easier to manufacture, easier to refurbish, safer to fly. This continuous improvement is essential for moving from experimental test flights to routine operational missions that can carry precious cargo, and eventually, human passengers. A key part of this future is reusability. And a key part of reusability is the colossal launch tower, nicknamed Mechazilla. Its purpose is audacious. It is designed to catch the returning super heavy booster using giant robotic arms. This maneuver, if perfected, would be one of the most incredible feats in engineering history. Catching the booster eliminates the need for heavy landing legs, saving weight that can be used for payload instead. It also allows for much faster turnaround, potentially relaunching the booster within hours. Each test brings them closer to attempting this catch, a milestone that will truly define the next era of rocketry. The work at Starbase is a powerful symbol of human ambition. It is a place where science fiction is slowly but surely being forged into reality. The construction of new ships like Starship 37 and the development of Block 3 designs are tangible progress. They are the physical manifestation of an iterative design process. With each new vehicle, the dream of a fully reusable launch system gets a little closer. This factory is not just building rockets, it is building the foundation for our expansion into the solar system, one stainless steel ring at a time. The next flight of Starship has a clear set of ambitious goals. These are not just about reaching a higher altitude. They are specific, technical milestones that pave the way for future operations. One of the primary objectives is to test the payload bay door and deploy a batch of new Starlink satellites. This is a critical capability. Starship is designed to be the workhorse for deploying the next generation of these satellites, called Starlink VIF-3. A successful deployment would prove that the vehicle can serve its first commercial purpose, opening the door for a rapid expansion of the global internet constellation. Another vital test will happen in the cold vacuum of space, an in-space engine relight. After the main engines cut off to reach orbit, one or more Raptor engines must be able to restart. This is absolutely essential for future missions. It is the maneuver needed to change orbits, to head towards the moon, or to begin the journey to Mars. It is also a critical step for the return trip, allowing the ship to position itself for re-entry into Earth's atmosphere. A successful engine relight in space would be a huge step forward, demonstrating a level of control and capability far beyond a simple launch. Finally, the mission must end with a safe landing. While the ultimate goal is a soft landing and recovery, the immediate objective for the ship is a controlled splashdown in the ocean. This tests the vehicle's ability to survive the fiery heat of re-entry and to execute complex aerodynamic maneuvers using its flaps. For the Super Heavy booster, the goal is a soft splashdown in the Gulf of Mexico, bringing it one step closer to being caught by the Mechazilla arms. Each successful landing, even in the water, provides invaluable data for perfecting the process, making the system more reliable for the future. These milestones, satellite deployment, engine relight, and a controlled landing, are the building blocks of interplanetary travel. They are not just items on a checklist for a single flight. They represent the fundamental capabilities a vehicle needs to operate as a true space transportation system. Proving these abilities is what will transform Starship from an experimental prototype into a reliable rocket. It is how we will build the infrastructure for a permanent human presence on the moon and take our first tentative steps toward becoming a multiplanetary species, exploring new worlds in our cosmic neighborhood.